Welcome everyone. Welcome to this session. I'm Alessandro Bellini. I'm your host for the next 30 minutes. And this session will be about virtual prototyping in the life sciences. So let's see a video. Now let's talk about industry challenges. Of course, here we have to take into account the complexity of a patient. So the optimal patient experience is personal, very hard to engineer. The cost of innovation, very escalating in this time. And of course, regulatory compliances. So in this case, there is a risk focus on it. And these are the main challenges for the life science industry. Let's talk about the actual workflow for the companies. Now, it takes years to go from a design, bench test, various bench tests, animal test, cadaver test, animal trial, and so on, finally reaching a clinical trial. And this is very risky and very high cost. So in this case, the development and validation paradigm is predominantly physical. This is a major contributor to the timeline, to the cost, quality, and risk. What we can provide with modeling and simulation is another approach using what we call in silico. In silico means at the computer with a digital environment. We can reduce to days and months with the upfront testing in a realistic human environment all the workflow. So in this case, from the design to in silico bench test to human modeling and clinical trial, we can develop defensible validation or regulatory evidence in days instead of years. So this is a major change of the validation dynamic. More model-based in silico validation upstream and more quickly, so completely evaluating the product before the clinical trials. What we can do about in the life science? We can, of course, provide the ability of change management and pedigree repository for reusable patient models. We can couple the device model with a virtual human model to create a virtual clinical test. So that's why we are talking about a virtual human modeling and virtual prototyping. We can provide the infrastructure and management for conducting in silico clinical studies of multiple configuration device patient combinations. As you can see, we can approach in this case to dental with the implants, procedures, and so on, ears coupled with hearing aids, dynamics, acoustics, of course the brain coupled with the devices, drug, and so on. Eyes, so coupled in this case again with devices, corrective procedures, and so on. The heart, this is very important, with pacemaker leads, valves, angioplasty rings, mitral clips, and so on. Joints, bones, coupled with motion simulation, articulation, loads. Skin, coupled with needles, attached device for penetration, for fluid injection, and so on. And of course, the body as a whole. So now let's see a video.
Je suis motard et j'aime la liberté que ça m'apporte. À Montauban et en Bretagne, quand j'étais jeune, je réparais des motos. C'est une passion qui ne m'a plus quitté. La mécanique moto, c'est un peu comme la chirurgie, il faut être très précis. Ce sont des disciplines à la fois intellectuelles et manuelles, où le cerveau guide la main. Je suis Bruno Ferré, chirurgien orthopédiste et cofondateur de Digital Orthopedics. Notre mission est de transformer le diagnostic et le traitement chirurgical des pathologies ostéo-articulaires, notamment grâce à l'utilisation d'outils de modélisation, de simulation et d'aide à la décision clinique. Ça permet une compréhension globale et inédite de l'état du patient et d'apporter un traitement optimal. C'est une révolution majeure. En tant que médecin, j'ai le devoir de servir le patient, de mieux le soigner. Ce que j'aime par-dessus tout, c'est le contact humain de la consultation, les rencontres avec les vrais gens. C'est le sel de ce métier fabuleusement riche et humain. Grâce aux outils que Digital Orthopedic propose, nous sommes en mesure de simuler et tester l'opération future avant l'acte chirurgical. On peut ainsi prévoir si elle aura les effets attendus et limiter les risques pour les patients. Il faut faire avancer la médecine, surtout pour les générations suivantes. Pour ça, il faut continuer à chercher, rester curieux, comprendre. Seule la science et l'innovation peuvent nous aider à progresser. Depuis longtemps, on utilise des outils de modélisation et de simulation pour concevoir des avions. Mais on peut faire des choses fantastiques pour la santé également avec ces solutions. C'est donc vraiment important que les ingénieurs et les médecins collaborent pour qu'une nouvelle médecine voie le jour. Quand je regarde derrière moi, je ne pensais pas faire tout ce chemin en me lançant dans la médecine. Mais une chose est sûre, l'orthopédie avance à pas de géant et je suis heureux de pouvoir accompagner la transformation de ce métier.
So very interesting. Now we are talking about Abacus knee simulator. It's a specific module for Abacus where we can approach to this type of analysis with modules. So for example, contact mechanics, implant constraint, tibiofemoral constraints, the basic of a knee loading. So I mean, of course, with all the complex situation, all the complex mechanics that we have, and the VR simulator. Let's review it one by one. So let's talk about contact mechanics. Here we can analyze the basic contact pressure and area distribution between femoral and tibial components. We have the ability to include only the implant, the ability to set as a deformable, of course the platform type, so it's if it's fixed or rotating, the compressive load, and we can choose also the flexion angles. So in this case, of course, we will have multiple degrees of freedom for the medial lateral translation, internal external rotation, and the varus valgus rotation. In this case, if we are approaching with the physical testing, it costs up to $14,000, and the time spent is about 4 weeks. Instead, with the Abacus knee simulator, we can do it in 10 minutes the setup, and from 20 to 3 hours, 20 minutes to 3 hours the analysis. So it's a very important return of investment. We can talk about implant constraint. So in this case, we are analyzing the laxity between the femoral and tibial components. And in this case, again, we can have a specific model for this analysis, again with the flexion angles and the laxity test. So we can input what are the maximum anterior displacement and posterior displacement. Again, here we can see which is the cost for a physical testing, $7,500, and again 4 weeks for completing a test. And on the contrary, in Abacus, it's up to 10 minutes just the setup, and from 30 minutes to 12 hours the entire analysis. So very, very important. Let's go on with the tibiofemoral constraint. So here we are adding another layer of complexity to the analysis, and we can again analyze the laxity of the tibiofemoral joint with soft tissue. So you can see that we are including the ligaments and adding to the implant, and we can define which are the ligaments that we are interested to, and again the boundary condition about the laxity test. Also here for each and every ligament we can define the pre-strain and the linear stiffness. Very important to define the specific patient situation. And also the bone shift for the femur. Here we actually there is no equivalent standardized test. It's a very complex test, and again in Abacus can be done up to 12 hours with just 10 minutes of setup. Wear simulator. Here the prediction is similar to a fatigue analysis for components. We are predicting the wear of the tibial insert over a number of cycles. So here we have the bumper parameters, the wear output, so the how many cycles we are calculating, and here you can see that the cost for the test is very expensive. We are talking about $100,000 and a lot of time, because there is involved a lot of cycles, so it can take up to 12 weeks for completion. Instead, in the Abacus knee simulator, we can do it up to 6 hours. Also, we can analyze the basic TKR loading. Here we have the whole knee joint performing daily activities. So all the ligaments, the femur, the implant, but also the mechanics of the muscles. Very important here because we have a very complex model with quadriceps, patella, patellar button, patellar tendon, and so on. And again, we can define which are the movement that we can test into this model. And of course, again, we can define all the ligaments properties and the muscle properties now, with also the bone shift. And here you can imagine it's a very, very complex situation. There is no equivalent standardized test available, and still in Abacus knee simulator can take just 15 minutes to set up and up to 24 hours to do the calculation. So now let's look at this video.
This is the living heart demo. You start in an operating room environment. You then walk up and stand beside the patient as if you're going to operate on them. You will notice there's a control panel in front of you which has 3 sections that control the viewing of the skin, skeletal, and circulatory layers. As you point at a layer and click the trigger button, it changes from green, signifying enabled, to blue when the layer is not being displayed. You can change the orientation of the patient so they're standing up in front of you. And notice that as you point at a specific structure on the patient, a small text box appears informing you what you are pointing at, the specific bones in this instance. And here we have isolated just the circulatory system. The tracking system is constantly adjusting the model in relation to your head movements, and when you are standing in the system and wearing the track glasses, it looks as if you are standing next to the patient. Now we're going over to the viewing screen showing the patient information and history, including their MRI, CAT scan, and EKG, which are then fed into the Simulia software to build a 3D model of their heart. This model would live in a cloud-based environment to allow for collaboration with specialists anywhere in the world. This is the rendered 3D model of their heart, and this is an actual model of a 39-year-old male patient who has no medical problems. You can move around and look at various angles into the heart. This is a horizontal cross-section of the patient's heart. When you're standing there, it appears as if you are standing knee-deep in the heart, looking down into it. This is a vertical cross-section of the heart. And this is the electrical impulse model of the heart. This shows the electrical stimulation provided by the nervous system, triggering the heart muscles to move. We're now going to take a ride through the heart, following the path of blood flow. We start outside in the veins, being pulled into the heart, pushed through the lungs, and then pulled back into the heart, and then pumped out to the body. As you can see, there's a text box in the center of the display, which tells you where you are in the heart, showing which chamber we're in and which valve we're passing through. If you stop moving and use the pointer, you can highlight areas of the heart, and a separate text box appears telling you what you're pointing at, making this a fabulous teaching tool. Here we're about to go through the pulmonary valve and then out to the lungs. And here we're flying through lung tissue and going back into the heart, dropping down through the mitral valve. And here we've stopped moving and I'm pointing at the mitral valve. You can see the separate text box and the chordae tendons light up when you point at those. And now we're going to go out through the aortic valve to the aorta and then distribute it out to the body.
Now we are talking about the heart and all the devices that we can analyze in conjunction with all the cardiovascular pathologies or medical devices or medical imaging, vaccine, and so on that are involved in this case with the circulatory system. Speaking about Simulia fluid solution for life sciences, we have the ability to use transient to analyze transient computational fluid dynamics, the drug injection and diffusion into the blood vessels of a patient, of that particular patient. Of course, two-way full fluid structure interaction in the large arteries, for example, steady state of blood flow. And also we can move on to peristaltic pump or heart valve and so on. Which are the challenges of blood flow simulations? Basically, blood behaves as a non-Newtonian fluid. It's not like water, so we are calling it a shear thinning fluid. mostly it's unsteady. We have to analyze a pulsation of the flow. Of course, the regime is it's transitional between laminar and turbulent. We need a very accurate mesh with a high-quality prism layer for reproducing accurately the boundary layer. We need also fluid structure interaction because the wall of arterials are flexible, and we need to take into account that behavior. And the boundary condition depends heavily on the resistance and impedance of the vasculatory system. So we can couple the boundary condition with a lumped parameter network or a concentrated mass network if you want. And we can also take into account that we need a patient-specific modeling. We need the model of a vasculatory system for that particular patient. So, for example, we are talking about blood flow simulation, and here you can identify that with our solution we are able to analyze the flow in a steady regime, in a transient fluid regime. We have the ability to understand also the fluid structure interaction between, you can see from the structural from CFD analysis. We can extract automatically the fluid volume with automatic hole search and patch. We can couple the structural analysis here, the finite element analysis, for example, with the CFD. We already said with the fluid structure interaction. So again, here I'm analyzing the CFD result, so the blood flow result, and then I would like to see what is happening to the wall of the blood vessels. And this deformation of the blood vessel walls can, of course, influence the CFD result. So again, this is a complete, a full integration of fluid structure interaction, and coupled also with the lumped mass network. We can analyze the delivery of drugs and diffusion in a particular blood vessel of that patient. So from MRI scanning, we can define the model of the blood vessel of that patient, and we can define the CFD analysis inside these vessels to provide the drug delivery, to understand what is going on with that kind of drug. So wide range of modeling capabilities, non-Newtonian fluid models, active and passive multi-species, porous media, of course, and of course we are talking about transient analysis here. Let's take into account also an heart valve. In this case, we have in X-Flow, we had the ability to couple it with Abacus, again, to make fluid structure interaction. So you can see we are capturing large deformation and pinching of the heart valve, and what is the effect on the blood flow. Now let's have a look to an example about peristaltic pump on 3DEXPERIENCE platform. Here we have the simulation of a peristaltic pump. This is the structural model. You can see a casing with a roller inside. The roller, the rigid roller, is frictionless, and we have an elastomeric tube with a hyperelastic material. So we have something that will move and deform the tube in order to create a fluid dynamics behavior. On the structural simulation, we will have Abacus explicit with general contact. The simulation time is 5 seconds with automatic time incrementation and mass scaling. Here you have a compression of the tube, so we are using an hyperelastic material. And the compression is defined as the final tube gap divided by the original diameter. We have the roller rotation, of course, that is the impulse that is going on, ramped, and the velocity is ramped from 0 to the maximum over 0.2 seconds. So that is the starting of the motor. In the fluid model, we have the inside domain of the tube with water in this case, and a turbulence model that is called realizable K epsilon. We can choose other turbulence model as well. This is the model that we are using for internal analysis. And the openings at the end of the tube, so they are defined as stagnation inlets with zero gauge pressure. So in this case, you can see from the animation what is going on. So the rigid bar is rotating, creating this impulse that is deforming in different position the peristaltic tube. So you can see that from a structural point of view, we have a rotating stress all over the structure and the compression over this portion of the tube. From fluid dynamic point of view, we can see the gauge pressure. So we are compressing the tube, and we are creating two different regions. One is basically it's a low pressure, at a low pressure, and another one that is a high pressure. So the difference in pressure is creating the velocity that is moving the water inside. And you can see also with the mesh, the default mesh motion settings, a good job maintaining the integrity in the cross section, including the boundary layer. Here again, you can see some other results in terms of velocity vectors, and the pulse that we can see in terms of the time. So either from mass flow point of view or velocity point of view, you can clearly see what is the pulse and which is the extension of the pulse. So now let's hear from General Electric, from GE Medical, what they are using about simulation in the life science.
And then eventually we ended up in using structural performance engineer, which has the abacus implicit solver. And how we have done is, because our vaporizer ventilators are very important. Next few slides will show it for you. So as Ramesh mentioned, the workflow is very important. Like Omar mentioned, we got to follow the process easily. This structural performance engineer is having wizard-like structure. We started from setting up the model, especially what type of scenario, and setting up the parts which are contributing this analysis. In this case, top block, which is made up of aluminum, bottom chamfer, Teflon, and O-ring is an elastomer. And we use visualization management on and off to turn the model on, model off. For example, I have to plan the analysis correctly in order to give Dr. Joe and our team very good results. So I started using a model preparation app and created a point where I am going to apply my prescribed displacement as shown in this screenshot. And we got to have a good mesh in order to have a realistic simulation. So we love this meshing coming out of structural performance engineer, Doctor.
Yeah, the meshing tool here is pretty amazing.
And then Dr. Joe asked me to run in my laptop because everything is cloud-based. I'm not using my laptop. So we created around 600,000 elements, and you see the details, how the elastomer is modeled using brick elements and all the parts like metal, bottom and the top, everything we took care of brick as well as tetrahedrons. So you see from here, we can solve it through cloud or we can solve it through embedded system. So I used my embedded system license, solved it very quickly under 3 to 4 hours. We use generalized contact very often. We took care of all the loading conditions precisely by working with our design team, especially Joe Bexton is our senior design team leader here. So I worked with him, cut the model, plan accordingly, just push the button.
And one thing I'd like to point out we're doing this modeling to drive the design. This isn't we designed it and then let's just see if it's okay. This isn't an analysis problem. This is a engineering design problem. Very impressed with its capabilities.
Yep. Next slide. We are going to see the animation of how the stress. See how beautifully the nonlinear simulation is coming up, and we are able to compress it. We have done this exercise first time in our ARC in Madison, Doctor.
Yep.
So we are around 100 years old. Dr. Joe came on board a couple of years ago, and then I came here to assist him and our team. So we are able to show the engineering design review and our chief engineers how this tool is helping us to see the animations, how the product is behaving before we come up with the final design. Yes, Doctor. Next one is the contact pressure. So Abacus provides a lot of visualization option under post-processing. I can put one part in transparent mode, another part see the contact pressure, how it comes. And most important thing, which is shown in the next slide, our design engineer and the design team member looking for how much force needed to push it. So we were able to calculate from the point I created.
Okay, so this is the end of my presentation. I hope you enjoyed. Stay for the question and answer session and enjoy the rest of the 3D Experience World 2021. Goodbye.